Okay, today we're going to find out how to get derivatives of functions like this. Which are the product of two functions. It'd be very nice if it were as simple as when you add two functions. Recall when you add x cubed plus sine of x, you just take the derivative of x cubed, 3x squared, plus the derivative of sine of x, cosine of x, and add those together. So it would be really neat if the derivative of this thing is just the derivative of the first times the derivative of the second. Okay? Is that true or not? Well, let's just check something else out and see what happens. Let's consider the derivative of x cubed times x to the fourth. Okay? What's the derivative of that? Well, if we use this idea, it's going to be the derivative of the first. I'm going to put a question mark here. It's going to be the derivative of the first, which is 3x squared, times the derivative of the fourth, which is what? 4x cubed. And you multiply those together and you get 12x to the fifth. So if this is correct, this is what we get for an answer. However, x cubed times x to the fourth is x to the seventh. And we know that the derivative of x to the seventh is what? 7x to the sixth. So apparently not. This is not the case. Taking the derivative of the product of two functions isn't this easy. So, since that's not true, what is the case? Well, here's the answer. It's called the product rule. And the product rule says if you want the derivative of the product of two functions, I'm not going to give you the answer. I'm going to prove to you the answer. Remember what the definition of the derivative is. The derivative for any function is the limit. Here's one of our ways we expressed it. As t approaches x of f of this function evaluated at t minus this function evaluated at x all divided by t minus x. And never lose track of what we're doing here, okay? Remember, here's your function, whatever it happens to be. Here's x. Here's t. So this is this value minus that value. That vertical distance there, the change in the y values, is the change in the values of the function, divided by the change right here, t minus x, and then you take the limit as t approaches x, and that gives you the slope at this point. Okay? Gives you the slope there. So that's what we want. And we're going to assume that f and g are both functions for whom we can take the derivatives at any point. They're called differentiable functions, where we can take the derivative anywhere. So the limits of the individual ones, the derivatives of both of these things exist on their own. Okay? So what do? Here's what we do. We say, well, we need a trick. As we've done before, remember when we wanted to find those limits, we often did something kind of clever by multiplying and dividing by the same thing. So we multiplied by a fancy form of 1. Here we're going to add a fancy form of 1 to this. Watch this. I don't know who came up with this. Someone smarter than me, but it's pretty clever. I'm going to subtract f of x times g of t, and then I'm going to add f of x times g of t, and then finally I'm going to subtract this thing again, minus f of x times g of x. Okay, now you might say why? Whenever a student asks why, there's two different questions they could be answering. They're saying, why is that valid to do it? In this case, it's valid to do it because I'm just adding 0. This thing minus this thing is 0, so I haven't changed anything at all. The other question they might be asking is, why would you want to do it? And that's a deeper question. In this case, here's why you would want to do it. Because I can now write this as I'm going to do a couple steps of algebra here. If you have something of the form a plus b over c, you can write that as a over c plus b over c. Remember that? That's true. That's valid. So right here, I'm going to take this thing right here divided by this, and when I do this, I'm going to factor the g of t out from these two. So I'm going to write it like this: f of t minus f of x all over t minus x all times g of t, plus, do the same thing here. I'm going to factor in f of x out the front, and I'm left with g of t minus g of x all over t minus x. Right there. Okay? Now, what happens as we take the limit of this whole thing? Well, let's see. Does this look familiar? This is just the derivative of f at x. That was the definition of the derivative. So this is f prime of x. Here we have the limit of g of t as t approaches x. Now, as I said, we're assuming that f and g are differentiable functions. The derivative exists everywhere. And since the derivative exists everywhere, they also have to be continuous. Just think about it. If you had a function which wasn't continuous, let's just take one example here. I'm not going to prove it to you rigorously, but if it isn't continuous, then what happens if I want to take the derivative at this point? At this point here, the y value, if I take from here to here, and I take the change in the y values over the change in the x values, notice what happens. Instead of, in normal situation, if you go from here to here, both the x and the y value approach 0. They both approach 0. Here, the y value wouldn't be approaching 0, but the x value would. So remember what happens? If the y value stays big and the bottom value goes to 0, that goes off to infinity. So if something doesn't have a derivative, then it can't be continuous. So in other words, since this thing does have a derivative, it is continuous, and to be continuous means that as t approaches x, this thing approaches g of x. So that just goes to g of x right there. Now we can do the same thing here. Here we have f of x, and here we have the derivative of g right there. So there is the answer. There is the formula for the derivative of the product of two functions. Let's write it down and then use it. So this is the derivative. I like to say it verbally. The derivative of the first times the second plus the first times the derivative of the second. And that's called the product rule, because it's obviously the derivative of the product of two functions. Now let's see if it works. Let's first try it on the one that we started with. Well, it's on this one right here. Remember, we wrote this as x to the, I forgot which order it was, x cubed times x to the fourth. And we want the derivative. And what does this say to do? It says you take the derivative of the first times the second plus the first times the derivative of the second. Okay? And if you do that, notice we have 3x to the sixth plus 4x to the sixth. 3 plus 4 is 7x to the sixth. And notice that 7x to the sixth is indeed the derivative of x to the seventh. So yeah, it works. As it had to, right? We just proved it. So let's go back to the first one I had here. F of x is equal to x cubed times the sine of x. And let's find the derivative. The derivative is what? Derivative of the first times the second plus the first times the derivative of the second. There you go. That's all there is to it. Okay, and again, never lose sight of what you're doing. This is a function. F of x tells you the height of the function. This right here tells you the slope of this thing at any point. Okay, let's try another one. Let's try f of x is equal to x cubed, or let's say make it x to the fifth, times the ln of x. Okay? Well, what would f prime of x be? The derivative of the first times the second plus the first times the derivative of the second. Derivative of the second, recall, is that. And there we go. So we can either write it like that, or you can go 5x to the fourth times the ln of x, plus this is going to be another x to the fourth. And so you can either leave it like that, or you can factor the x to the fourth out front and be left with 5 ln of x plus 1. It's kind of a matter of personal preference as to which you prefer. You basically want an answer which is going to be the easiest to work with all the way through. Okay, let's try a couple more. Let's try f of x is equal to the square root of x times the cosine of x. Okay, so for this one I'm going to first rewrite it like this. I write it as x to the 1/2 power times the cosine of x. And so now the derivative is going to be the derivative of the first times the second plus the first times the derivative of the second. Derivative of cosine, recall, is negative sine of x. So you have that right there. And again, you can pretty it up if you want to. You can write this as cosine of x over 2 times the square root of x plus, or let's bring the minus out front, minus square root of x times the sine of x. You can do that. If you wanted to, you could put, yeah, that's fine. You could put a square, yeah, I'll leave it like that. That's as good as any. Okay? Let's try one more. How about e to the x divided by x cubed? Okay, now notice this is a product rule, whereas here I have the quotient of two things. However, I can write it as a product of two things. I can write it as 1 over x cubed times e to the x, which is the same as x to the minus 3 times e to the x. And so now you take the derivative, and let's see what we get. Take the derivative of the first, negative 3x to the minus 4 times e to the x, plus the first, x to minus 3, times the derivative of e to the x. The derivative of e to the x is just e to the x, recall? So you get that. So you can leave it like that, or again, I don't like negative exponents myself. I like to put them down in the basement. Just it's easier to kind of see what's going on. Like that. And then you could either leave it like that, or I would prefer it like this. I will multiply both the top and the bottom by a power of x. And now that I have that, I can combine this as one fraction. So I have negative 3 e to the x plus x e to the x all over x to the fourth. And then I can factor the e to the x out in front, and I'm left with x minus 3 all over x to the 4th. Okay, so there's my final answer. Okay, very good. So, as long as I've got a quotient of two things, let me show you the quotient rule. The quotient rule, similar to the product rule, allows you to find the derivative of the quotient of two functions. I'm going to leave this here as just the answer that we had for this, and we're going to find the we're going to use the quotient rule on this in just a moment. So let me first give you the rule, the quotient rule. It says if you have f of x divided by g of x, and you want its derivative, well, it's similar to this one. Here we took the derivative of the first times the second, and so on. Here we start with the first. The first is the top. The derivative of the first times the second. Here we had a plus. Here we have a negative. Minus the first times the derivative of the second. Okay, I just think that a dividing sign has a little negative hidden in there, so it just reminds me that it's a negative there. So that's it, but there's one more piece to it. I divide it by the square of the denominator. So it turns out if you wanted to go through the proof, that's what the answer is. That's called the quotient rule. Okay, so let's try it on our quotient problem. Here we had f of x was equal to, what was it? It was e to the x divided by x cubed. So the quotient rule says, okay, you want to do enough of these that you just can roll them right off your tongue. The derivative of the top, the derivative of e to the x is e to the x. The derivative of the top times the bottom minus the top times the derivative of the bottom. The derivative of x cubed is 3x squared, all divided by the bottom squared. Bottom squared is going to be x cubed times x cubed, which is x to the 6th. Now notice we can factor a e to the x and also an x squared out of both of these. And we're going to be left with an x here. We're going to be left with a 3 right there, all over x to the 6th. And here we have x squared. Here we have x to the 6th. Two of those divide out. You're left with a 4 there. So it's e to the x, x minus 3, all over x to the 4th, which is what we had before. There you go. Let's do some more. Again, you want to do enough just to be able to do it fast without even having to think about it. Let's let f of x be equal to, let's take ln of x divided by cosine of x. Okay? The derivative is going to be what? The derivative of the top times the bottom minus the top times the derivative of the bottom. The derivative of cosine is minus, there's the minus right there, sine of x, all over the bottom squared. I'm going to write it, I could write it like this, but you can write it without those parentheses by doing this instead. You put it right in there, means the same thing. Okay, so there's that one. Let's try another one. How about the derivative of tangent? We haven't found the derivative of tangent yet. All we found is the derivative of the sine and the cosine. But hey, that's no problem. We know how to write tangent in terms of sine and cosine. That's the definition of the tangent. And so the derivative of the tangent is going to be straightforward. The derivative of the top times the bottom minus the top times the derivative of the bottom. Derivative of the bottom, again, is going to be a negative sign. There's the negative. there's the sine of x all over cosine squared of x. And you could leave it like that, but I think there's a much better way. Notice that this is cosine squared plus sine squared. And remember the trig identity? Cosine squared plus sine squared is equal to 1. So this is just equal to 1 over cosine squared of x. And you could leave it like that, or since 1 over the cosine is the secant, that's the same as the secant squared of x. Quite often authors will write it like that. I personally prefer this one, but either one is fine. Okay, and as long as we're talking about secant, let's just do one more. If f of x is equal to the secant of x, that of course is 1 over the cosine. So the derivative, what does the derivative say to do? You take the derivative of the top, derivative of 1 is 0, times the bottom, minus the top, times the derivative of the bottom. The derivative of cosine is negative, there's the negative, negative sine of x, all over the cosine squared again. So that's equal to sine of x over cosine squared of x. Again, you could leave it like that, or the way it's typically written is you write this as 1 over cosine of x times the sine of x over cosine of x, and 1 over cosine is the secant of x, and sine over cosine is of course the tangent of x. So it's kind of an interesting function. The derivative of secant is itself the secant of x times the tangent of x. So there you go. That's the product rule and the quotient rule. And so that allows us to find the derivatives of all sorts of functions. The only kind of function we really don't know how to get yet is something like this, the sine of x to the 5th. That's different from this, of course. This is the product of two functions. This is the composition of two functions. Here you're just multiplying them together. Here you're first sticking x into one function, and then you're sticking that into the other. So in the next lesson, we'll find out how to find the derivative of this thing. It's called the chain rule. You'll see why that's an apt descriptor of that particular formula. Okay.